This is the lecture for Module 3 of Unit 5. This module introduces the concepts and ideas of conjugate acids and bases. Alright, first let's begin with a definition. Each acid has a conjugate base. This is what is left after it loses H+. All we often call H+, a proton, a hydrogen atom without its electron. Well, after an acid loses its proton in water, the formula loses an H atom and the charge decreases by 1. For example, HCl goes to chloride. Each base has a conjugate acid. Add H to the formula of any base and the charge increases by +1. Alright, so given these definitions, or ways of determining conjugate acids and bases, you should be able to determine the conjugate base of formic acid and the conjugate acid of the well-known weak base ammonia. Take a moment to look at these definitions and then attempt the answers before moving on. The conjugate base of formic acid is CHO2-, take away the H and take away a positive charge or bring the charge down by 1. It should be no surprise to you that the conjugate base of formic acid is called the formate ion. And the conjugate acid of ammonia is found by adding a hydrogen atom and increasing the charge by 1 to +1. So the conjugate acid of ammonia is ammonium. The conjugate is formed, again, when the acid or the base reacts in or with water. Recall that formic acid reacts with water or breaks up in water to some extent to make formate and H+. It doesn't do that 100% because you know formic acid is a weak acid, and you know ammonia reacts with water to make ammonium and hydroxide, although the left-hand side of this reaction is favored. Right, so the conjugate species forms when the acid or base reacts with water. In this sense, you can see that water acts as an acid, or it can act as an acid or base in various chemical reactions. The Bronsted-Lowry definition of an acid is any substance that can donate a proton, and a base is any substance that can accept it. Consider the reaction of ammonia and water to make ammonium and hydroxide. In the forward reaction, NH3 is a base, accepts a proton to become ammonium. And water is acting like an acid. It's donating the H+. In the reverse reaction, ammonia donates a H+. Hydroxide accepts an H+ to form ammonia and water. So notice, you begin to see that this name is not exactly, not just a formal name. Here we have a reaction in which this conjugate acid, ammonium, reacts like an acid. Again, the acid is any substance that donates, and a base is any substance that accepts a proton. There are base and acids in both the forward and reverse reactions, according to this definition. If you explicitly show water in the equation of the dissociation of an acid, you can see that it acts like a base. In other words, let's write the form for the reaction of acetic acid so that it shows hydronium and not H+. And then you have to add a water to the left-hand side. In the forward reaction, this donates an H to water and acts like an acid, and water acts like a base. Again, in the reverse reaction, hydronium acts like an acid, and the conjugate base, acetate, acts like a base. So again, a conjugate base can react with an acid to make its conjugate acid in water. Okay, you've seen or just saw an example in which the conjugate base acetate reacts with acid in the Bronsted sense. The conjugate base can act like a base with water as well. Acetate can react with water to make acetic acid and hydroxide. Here the conjugate base acts like a base and water acts like an acid. Okay, we expect that this reaction favors the left, but let's see if we can find out what K for this reaction is. If you consider the reaction of acetic acid with water, the equilibrium expression has hydronium, acetate, and acetic acid in it, and we've seen that this number is 1.8 times 10 to the minus 5. Likewise, for two waters breaking into hydronium and hydroxide, we've seen that K is hydronium times hydroxide is 1 times 6 to the negative 14. Alright. Now consider the reactions B and A, which I now show in bold and red. The top reaction, the one we would like to find K for, is equal to reaction B minus reaction A. In other words, if you take the reverse of this reaction, add it to this one, and cancel things that appear on both sides, you obtain this reaction. Therefore, Kb for this base is K for this reaction, Kw, minus, or divided by, I should say, K for this reaction, Ka. Kb is Kw of Ka, 5.6 times 10 to the negative 10. Okay. So the weak acid, or the conjugate base of the weak acid, is itself a weak base. Also, if you will consider this formula a moment, it should be clear, the larger Ka is, the stronger the acid, the smaller Kb, or the weaker the conjugate base. Alright. So mathematically Kb is Kw over Ka. Alright, so suppose you are asked to find the pH of 0.4 molar potassium nitrate. Here the problem reminds you nitric acid is a weak acid and provides you with Ka. Okay, here nitrous acid are weak acid, and nitrite, the conjugate base, is what we have in solution. Alright, the reaction of the conjugate base in this case would produce hydroxide and nitrous acid. Kb is Kw over Ka, so Kb for this base is 1 times 10 to the negative 14 over 7.1 times 10 to the negative 4, or 1.4 times 10 to the negative 11. You may find it helpful at some point to use the relation pKb is 14 minus pKa. You could have get to that by the same. You can find values of Kb by that formula. But once we have Kb and we know the concentration of nitrite, we can write down an equilibrium expression, set it equal to the equilibrium constant, hydroxide, nitrous acid in the numerator, nitrite in the denominator. We make the usual assumption that there are, hypothetically, none of these ions present initially, and 0.4 molar nitrite. Equilibrium concentrations of these species are X. Nitrite concentration is 0.4 minus X. Well, you try treating that like 0.4 since Kb is extremely small. (1.4 times 10 to the negative 11 then is X squared over 0.4. 5.6 times 10 to the negative 12 is X squared. X is 2.4 times 10 to the negative 6 is the hydroxide ion concentration. We can finish the problem. Remember, the question is pH by first finding the pOH, which is 5.62. pH is 14 minus pOH. 14 minus 5.62 is 8.38. So pH shows that we predict a basic solution, pH is greater than 7, for this conjugate base. Right? Again, because as Ka grows large, Kb grows small, the stronger the acid, the weaker the conjugate base. Now remember, HCl is a strong acid. Alright, 1.3 times 10 to the 6 is Ka, or something like that formally. If we insert that here, Kb is extremely small. Alright, since HCl is a strong acid, chloride, let me correct, is a very weak conjugate base, and we should not expect it to react with water to make any hydroxide. Since ammonia is a weak base, however, ammonium has some strength as an acid. And, well, to show this formally, we can calculate the pH of a 0.2 molar ammonium chloride solution. Alright, the chloride is essentially a spectator, just like the potassium at the previous problem. So we are concerned with the concentration of ammonium acting like an acid. If ammonium acts like an acid in water, ammonium and water form hydronium and ammonia, the conjugate base of ammonia. Ka is Kw over Kb. Well-known Kb for ammonia is 1.8 times 10 to the negative 5. Or we have an equilibrium constant of 5.6 times 10 to the negative 10 for ammonium acting like an acid. Alright, the corresponding equilibrium expression for ammonium acting like an acid has ammonia and water in the numerator and ammonium in the denominator. Again, we assume a hypothetical initial state, no protons, no ammonium, 0.2 molar ammonium, products increase by X and reactant decreases by X, and naturally, since K is small, we will assume 0.2 minus X is small compared, well, X is small compared to 0.2, so that we can essentially treat this number as 0.2. Alright, this gives 5.6 times 10 to the negative 10 is X squared over 0.2, which gives a value of X of 1.1 times 10 to the minus 5. And remember, the way we defined X, it's equal to the H plus or hydronium ion concentration. This thing gives a pH of 4.98, indicating an acidic solution. So, because ammonium is the conjugate acid of a weak base, solutions of ammonium are acidic, just like a solution of potassium formate is basic. Alright, now let's think about this qualitatively. Consider solutions of each of the following compounds. You should be able to determine whether they are acidic, basic, or neutral. Try this for each of the solutions listed before moving on. Okay, again, the way to think about this is for each ionic compound listed, think about conjugate bases that appear within these species. Sodium is simply a spectator ion, for example, in sodium iodide. Iodide is the conjugate base of a strong acid, has no ability to act like a base. Nothing here can lose a proton, so this makes, beg your pardon, a neutral solution. However, in a case of potassium fluoride, K plus is a spectator, but taking fluoride, if we consider the conjugate acid, HF, we know that's a weak acid, and we might expect the fluoride to act as a base in solution, in which case fluoride reacts with water to make HF and hydroxides. We would predict a basic solution. Cyanide is the conjugate base of a weak acid, so potassium cyanide solution will be basic. Cyanide and water react to make hydroxide and HCN. Similarly, acetic in an acetate solution, potassium plays no role. Acetate is the conjugate base of a weak acid and will make the solution basic. In the case of cesium nitrite, cesium plays no role. Nitrite is the conjugate base of a very strong acid and has no ability to act as a base in solution. The solution will be neutral. Likewise, because bromide is the conjugate base of a strong acid, we predict a potassium bromide solution will be neutral. Right, this concludes the lecture on conjugate acids and bases.